Now, I will discuss some aspects of the general circulation and meteorology, in particular meteorology of the tropics and the water cycle. Now, this nice picture reminds us how complicated the system is. Just a second, I need to plug this in. I had forgotten the recording part of the ceremony. We have the simple conceptual model of evaporation from the ocean and condensation and rain falling and bringing the water back either directly into the ocean or over land. But of course the cycle is much more complicated, includes the terrain and vegetation and even ice, where the water can be stored for up to thousands of years, at least hundreds of years. Now, the atmosphere is mostly in the tropics. The atmospheric water is mostly in the tropics, as we see by this curve. By large, this is latitude. The equator is in the middle, and there is much less water vapor in the and water in the atmosphere than at high latitudes than here. And one way to measure the amount of water in the atmosphere is, of course, specific humidity, where we look at we count how many grams of water vapor there is in every kilo of water. Now, there are more ways of measuring the vapor in the atmosphere, and ways that are in many ways more convenient. We are always interested in the saturation and how far away we are from being saturated. Now, if we put some water in a bottle and we close the bottle and we leave it there for a while, the water will evaporate and we get vapor together with the dry air in here, and sooner or later the evaporation will come to an end, in the sense that equally many molecules go from the water into the air as they come back from the air into the water. And at that point we say that we are saturated, the air is saturated, and we measure the pressure of the water vapor, the gas form of water in here. We're not talking about droplets, just water vapor. And we say that this is the saturating vapor pressure. Now, this pressure is goes into the function where we define as R. We call it relative humidity, where the vapor pressure that we measure in the atmosphere divided by the saturation vapor pressure. And we usually think that 90% humidity is humid and 50% is dry, very dry. And the saturation vapor pressure is very much dependent upon temperature. And that's how we get the curve that we just saw. At 30 degrees, we have something like more than 40 millibars coming from the water vapor. While if we go down to 10 or we go down to 0 degrees, we have far less than 10. So there's a factor of 50 there from the ordinary cold climate to the tropics. So it's a factor of 5. And this explains that the curve showing the water in the atmosphere and the relative humidity as a function of latitudes, they are quite different. In the tropics we have peak peaks in both curves, but when we go to the subtropics, we have still quite some water in the atmosphere, but the relative humidity is low because the air is still very warm. While in the high latitude areas in the Arctic and high westerlies, we generally have high relative humidity, maybe not as high as in the tropics, but still high, but much less water. Because the air mass is cold. Now, this was a very simplified picture of the world. When we make these cross sections from the North Pole to the South Pole, we integrate, of course, around the globe. And of course, it all depends upon the governing wind patterns, land masses, and sea. But still, we see these nice regions here of relative humidity close to equator and up at high latitudes. We don't even have the Antarctica here, it's not taken into the picture, and we have the dry belt across there where we have the deserts. And the cloud cover reflects this quite a lot. But there are always interesting details in pictures like this. We can look at them for many, many minutes and always find something new, and even hours. You see that Greenland is sunny. It's very high up. Very sunny and nice place. At least sunny place. And we have some more details here in the western part of the Eurasia. It's quite different from when we get further east in terms of clouds. Now, the relative humidity has a signal that is opposite to temperature when we look at the diurnal cycle, where we have a diurnal cycle. Here we have the temperature moving up during daytime, and when the temperature increases and there's no extra humidity, extra vapor coming in, of course, then the relative humidity drops. And then during the night, temperature goes down and the relative humidity pops up again, and we get humid, humidity on the ground and even fog in some cases. Now, there's a long and winding road from water vapor in the atmosphere to rain. And this road is maybe particularly interesting because the road offers probably the greatest challenges in development of numerical weather forecasting. One of the interesting elements on that road are the aerosols. They play an important role in the formation of raindrops. And here we pick up the picture we had yesterday, reminding us of the scales, of the sizes of the elements that we are looking at. R is in micrometers. This is a typical small aerosol, a mini dust particle, if you like it that can act as a condensation nuclei for a typical cloud droplet. Then they grow to large cloud droplets first by condensation and then by collision. They collide with each other and form big rain droplets. Here at the bottom we see the curvature of a circular rain droplet. 10,000 times bigger than the tiny aerosol that contributed to starting up the phase change from vapor to liquid. Now, we had an interesting short discussion with our colleague from Mauritius yesterday, and do not hesitate to interrupt if you have any comments, or any of you, please. we have different composition of aerosol in the maritime and the continental air masses. There's much more aerosol coming from continents, from vegetation, from the ground, and to some extent from industry or traffic. Here we have some data to illustrate this. We have stratus, maritime and continental stratus. We have relatively big average drop size in the maritime cloud. In the maritime cloud we have fewer aerosols, and they tend to contribute to relatively bigger droplets and fewer. Here's the number of droplets in the maritime, and here is the number of droplets in the this is the continental, this is the maritime, and in the end we have approximately the same amount of liquid water in both clouds. In short, we have a lot more droplets, but they are smaller in the continental cloud. Now, how that is going to impact our weather forecast is a complicated matter, and how this impacts not just the weather forecast but the precipitation itself. We have been running some tests with modifying the number of droplets, and that has resulted in quite different quantities of rain. But the problem is always that we don't really know the true values of these microphysical variables. I'll spend 2 minutes on revising the theory of droplet growth, since this is relevant in this context. Here we have, on the x-axis, we have the sizes of droplets. These small droplets here contribute to haze. On this area here on the scale we have fog and clouds, and at the very end we grow into rain droplets. On this axis we have the saturation. This is 100% saturation, and this is supersaturated air. In this diagram we have curves, they're called the Köhler curves. They all more or less have this form, but they are different. Some of them go up, far up, some of them go slow, and each of these curves can be associated to a particular type of aerosol. The curves is an equilibrium for droplets. Droplets grow by following the curve. A droplet that for some reason starts to grow by condensation at this level, at this supersaturation, it will evaporate again until it meets the curve. The reason why is why we don't immediately get a lot of droplets when we pass the line of 100% saturation is most easily explained by energy considerations. We need some energy to create a new surface of a droplet. Anyway, our droplets they need to follow these curves, and when they grow big, the surface of the droplet is more or less flat, at least in the eyes of a new molecule that's coming and condensating on the surface. So that's for the theory of growth of droplets. When they grow a little bit more, the condensation stops, and they grow by colliding with each other. Again, we look at the graph of relative humidity, and the one we had yesterday, showing us the fluxes of humidity, vapor in the atmosphere. We I drew your attention to the fluxes of vapor that were opposite to the flux of sensible heat in the tropics. We have flux of vapor towards the equator or towards the intertropical convergence zone, while we have net flux of heat away from this area. When you go further up, further north, we have net flux to the north and no flux in the high north. So there's a net flux into this wet region of westerlies with propagating extratropical cyclones. So where do we have the precipitation according to this? Of course, we must have it in the tropics where we get all the influx of humidity. There's no influx of humidity into the subtropics. The flux goes either to the north or to the south. And in the westerlies, we have a lot of precipitation. And that's a nice map of precipitation in the world. Of course, the first thing we see is the layering north-south that we know with extreme precipitation close in the intertropical convergence zone and the dry zones, the subtropical dry zones. But there's more to it. We have variability which mostly is due to land masses and oceans, but there is a little bit more, and I cannot resist in showing you this. When we look at these things, one of the first things we ask is what is the scale of the data we are looking at? And the scale of this data is obviously so coarse that we don't see the 10,000 millimeters a year that we get in large areas, for instance in southern Iceland and in western Norway, which actually receive almost the same or even greater amount of precipitation than many parts of the tropics. This is from a numerical experiment that was carried out by Olafur, and we published several years ago. Even at resolution of 8 kilometers, the mountains managed to contribute to more than 8,000 millimeters of rain every year. In reality, we get about 10,000. And the reality comes from observations of snow. Now, I wonder how these gradients look like in the place we are now. It would be nice to see. I wouldn't be surprised if we had large gradients with all the mountains around us. Evaporation. Sunshine and dry air would be very nice, but the lower the humidity, the better, easier it is to evaporate. But of course, you need some water to be able to evaporate, and consequently, we do not get very much evaporation from the deserts, as we see here. But here's the winter evaporation in the southern part, very, very much, and very, very little, at least according to this map, in the north, and of course in the south. There are details in this. I won't go very much into that, but I actually suspect that in this region the evaporation may be, and in Antarctica may possibly be underestimated. It's very easy to believe that when you are in an area like this is a picture from December from Iceland, you get a lot of snow, and the snow just stays for days and weeks. It doesn't evaporate. It's very easy to believe that there's very little evaporation in this area. But as soon as the wind starts to blow, as it did yesterday, I got this picture yesterday, the snow starts to blow in rills, and then we actually get a lot of evaporation. Here you see that the sun is already high in the sky, and in December it was very, very low. It's great changes from day to day in this time. This is blowing snow on a road, and you see that the sky is clear. The sun is actually shining directly on the snow particles, and consequently this map may possibly be wrong in this area. This is maybe not a major topic for this seminar here, but it's interesting nevertheless. You may ask where the precipitation comes from to close the budget up there, and the answer is it comes from underestimation, systematic underestimation of precipitation when the precipitation is solid. Evaporation looks like this. Very good timing.
It's come from above.
Very nice. We have, of course, greatest evaporation where we have dry air and warm, sunny, coming over wet surfaces. Not surprisingly, we have a lot on each side of the tropical convergence zone. And there are interesting areas, as like for instance here on the east coast of Asia and at the east coast of North America. These local maxima are driven by warm winds, to some extent foehn winds that blow over the ocean and cause events of extreme evaporation. Not surprisingly, we have a budget that looks like this on a global scale. Surplus precipitation is greater than evaporation here in the tropics, and when we move out we get the opposite. We get much more evaporation in the subtropics, and then it rains and snows more up there in the north and in the far south, as we see from this. This is the budget, evaporation minus precipitation. A nice map, isn't it? With a lot of details. So, this is a very, very short summary of what I said yesterday in my lectures and the lecture today. We are dealing with a very small, very thin atmosphere on a rotating planet, very thin compared to all the mass on the Earth, and the greatest part of the mass is in the lowest part, in the troposphere. Yet the mass above is important because we often get perturbations up there that are going to propagate downwards and govern the weather in long-term weather. And different heating sets up circulations. The circulations close to equator, they tend to be to a large extent ageostrophic, and we'll come to that better tomorrow in our next talk. And when we